Welcome back to video 5 on vectors in 2 dimensions. We're now going to look at the magnitude of a vector. The magnitude is the length of a vector. If the vector v equals the component form a comma b, then the magnitude can be written the magnitude, or absolute value, of the vector equal to the square root of a squared plus b squared. If you think about this as the Pythagorean theorem, we know that a squared plus b squared equals c squared. And if we wanted to find the hypotenuse, or the diagonal, given the components a and b, we would take the square root of a squared plus b squared to find c. It's very similar if we turn this into a vector. That will give us the magnitude or length of the vector. You can conveniently think of this as the hypotenuse, as I said, since the two components will represent the two distances, distance in the direction, horizontal direction, distance in the vertical direction, to get from the initial to the end point of your vector. We now are asked to find the magnitude of the vector u with components -4, 3. Count to the left 4 and up 3. If those are my components, regardless of where on a Cartesian coordinate system you are sitting on, I can draw the vector as this vector, where I connect the initial with the final points. Now, I want to point out here that we're not looking at describing this, we just want the length of this diagonal. We want the length. So we're going to take the square root of 3 squared plus -4 squared. This will give me the square root of 9 plus 16. I happen to know this is a 3, 4, 5 triangle, which means I'm going to get the square root of 25, which equals 5. So the length, or magnitude, of my vector is 5. We'll call this the magnitude of u equals 5. For formality's sake, let's look at these algebraic operations on vectors. If we have a vector u in component form a sub 1, b sub 1, and another vector v with components a sub 2, b sub 2, the following are true. We can add the two vectors together and their components add together separately. You could also say respectively. The a's add together and the b's add together. If we want to subtract vector v from vector u, vector v's components subtract from vector u's components in a similar way. And if we want to scale the vector u by some constant, it will scale the x direction or component and the y component equally. So you can distribute that scalar. And if the vector u has components 1, -2, and vector v has component 0, 3, let's see if we can find 2v minus 3 times u. First, I'm going to list my vectors, 2 times the vector v, and that will be 2 times 0, 3. And then I will also list -3 times u, vector u, which will give me -3 times the vector 1, -2. If we think about this as separate components, I'm going to be subtracting 3u from 2v. And so I'm actually going to take this negative off, and I'm just going to perform the subtraction at the end. Notice that it will be like this example here. So let's calculate these separately. 2 times 0 is 0. 2 times 3 is 6. 3 times 1 is 3. 3 times negative 2 is negative 6. And now I'm going to subtract the vector 3 times the vector u from 2 times the vector v. That means I will have 0 minus 3, comma, 6 minus negative 6. And this will simplify further to negative 3, comma, 12. The 0 vector is the vector 0 with a little arrow on top. Sometimes it's bolded instead of having the little vector on top. And its components are 0, 0. And it plays the same role for addition of vectors as the number 0 does for addition of numbers. If you add 0, the number that you started with is still whatever it started as. So let's look at the properties of vectors for vector addition. If we add u plus v, we will get the same thing, or it is equal to v plus u. If we take the vector u plus grouping v plus w vectors, it will be equivalent to grouping u plus v and then adding the vector w at the end. If we add 0 to a vector, we still have the same vector. And if we subtract the same vector from itself, we get the 0 vector, which means there's no displacement. And now finally we'll have the rules for multiplication by a scalar. If you scale something with a constant out front when you add two vectors together, it's equivalent to distributing that scalar to both vectors. And if you add two scalars together and multiply it by the vector, it's the same as distributing the first scalar to the vector plus the second scalar multiplied to the vector. If you add them together, you get the same thing. Also, if you take two scalars and multiply them together, it's the same as multiplying them in different orders because multiplication is commutative, meaning you can change the order of C and D in this example, and it will come out with the same thing. Multiplying by a coefficient of 1 in front of the vector will not change the vector. Multiplying the vector by the 0 vector will give you a 0 vector, so no displacement. And if you multiply a scalar, C, times the 0 vector, you will still have the 0 vector. Also, just a note here, if you want to find the length of a vector, if you look at the magnitude of C times a vector, basically the C is a scalar, then you will get the same thing as if you find the magnitude of C multiplied to the magnitude of the vector u.